Hello, Year 8. What we're going to do in this lesson, lesson 3, is look at gravity and weight. So we need to return to our booklet, and in our booklet we've got this information which tells you about gravity being the force of attraction between pairs of objects. It also goes on to talk about this equation. So what we're going to focus on is this idea of what gravity, weight and mass are and how they are related. We're going to look at where this equation comes from, this relationship, by looking at this graph that we're going to complete. And then I'm going to show you how to, with missile floating and sinking, show you how to calculate the weight of objects and the mass of objects by using that equation and rearranging that equation. So quite a bit to do, okay, in this section. So what we're talking about here then is this idea that all objects with a mass have got a pull of gravity around them. So gravity is an attractive force. Now gravity is a very weak force. But the bigger the mass, the more gravity it has. Bigger the mass, more gravity. So if we take a small mass, like a ping pong ball, it will still have gravity attracting things towards it, but it will be very small and you wouldn't feel it. If you were to go to the moon and you would stand on the moon, and if you jumped up, then you would jump a lot further than you would do on the Earth, but you would be pulled down by the moon's pull of gravity. You would feel the moon's gravity because it's much larger. So the moon's got more mass, it's got a bigger pull of gravity. Now, if you go to the Earth has an even bigger mass, so it has an even bigger pull of gravity, which is why when you jump up on the Earth, you don't carry on going up that far, it quickly pulls you back down. Very difficult to escape the Earth's gravitational pull. Likewise, if we go to something that's even bigger, like the Sun, it's more massive. It makes up about 99.9% of the mass in our solar system. It's massive, basically, lots of mass. It's got a big pull of gravity, but it's pulling things in towards it. And in fact, the Earth orbits this Sun because it's being constantly pulled towards the Sun. Okay, the fact that it stays in an elliptical orbit around the Sun is a case for another lesson. So what we've got then is this idea that the bigger the mass, the bigger the pull of gravity. And if you want to look at why you weigh more on Jupiter and a little bit more about this, you can click on the link that I've included in the frog assignment. And this is a very good video from BBC Teach, only lasts 5 minutes. So, moving on. So, what we're going to do in our experiment, or the experiment that we would have done in class, is we would take a spring, a Newton meter. We would suspend that Newton meter from a clamp. I get my. We would have taken a clamp. We would have suspended our Newton meter on here that measures force, and we would have suspended slotted masses from this, and we would have recorded the force. We would have put 100 grams on there and would have noticed that we get a force on here of 0.98 newtons, and then we'd have placed 200 grams on there and we'd have got 1.96 newtons, and so on. What's actually happening now is that the Earth, because it's much more massive, has got a bigger gravitational pull. It's pulling the masses down, okay, and the masses are stretching this spring and giving us a reading. In fact, what this is saying is that for every 100 grams, the Earth is pulling with a force of 0.98 newtons. Actually, if we just round that up, we can say that if you've got 100 grams, the Earth pulls on it with 1 newton of force. So what we've got then is a set of results. And using those set of results, we can plot a graph. I'm just going to take a number of these. I'll take 0, 1.96 and 3.92. So if I want to plot a graph on here, rather than print this off, then I can go to Insert, Text Box, undo that, wrong place. So I'll put it there, Insert, Text Box, there we are. I'm just going to insert a capital X. I'm going to first of all put that text in front of text. What I'm now going to do is I'm just going to get rid of the outline. So outline, no outline. I want no fill. I want no fill. So I can now move that around. Oops. There we go. So I'm going to place that there on 0, 0. And then I'm going to find my other points. Copy, paste, paste. So 1.96 when we had 200, we had 1.96, so there's 1.5, 1.6, 1.96 there. And then I have 3.92, so that was for 400, 3.92. Now, I'll leave you to carry on with that. Now, what we can do then is we can plot a line, put a line in there. And this is where it does start to become interesting. So we can insert a shape, and that shape is going to be a line, and it's going to go from there. It's going to go through all my points, like so. And I'm just going to put a bit more weight on that. There we go. You can see a little bit more clearly. Now, what happens here is this gets interesting. Because if you look at what we've got weight on the y-axis and mass on the x-axis. We've got this line here. So if we go to this, what we can see is we have got this line here. Now, if this is x and this is y, if I want to calculate how steep this line is, I calculate the gradient on a hill. Now, the gradient here will be the change in y over the change in x. So I take this point here and call that x1 and call that y1, and take this point here and call that x2 and call that y2. What I can see is the change here is going to be the big one minus the little one, so it'll be y2 minus y1 over change here, which is going to be x2 minus x1. Now, taking this a step further, rather than x and y's, what we've actually got is we've got mass here and we've got weight. And we've got this line there, that's our gradient there. Now, our gradient, we've just said from here, is actually equal to the difference in y over the difference in x. So our gradient here is equal to the difference in weight over the difference in mass. And that gradient there is actually equal to, because it's weight and mass, gravity. Now, if we were to take another line and find another gradient, like so, and it was steeper, what planet do you think that might represent the gravity? What gravity do you think What planet do you think that is? Or which satellite do you think has a gravity that looks like that? So what we've got then is we've got mass on the x-axis, weight on the y-axis. We have the gradient as being equal to the change in weight divided by the change in mass, which actually is gravity. We can write that down here. Gravity is equal to weight over mass. Now, I'm going to move this. So to make W the subject. So if I multiply both sides by mass, what will happen here is that mass will cancel with that mass to leave W, and that will leave with mass on that side. So I'll end up with this mass times gravity is equal to weight, which is what we've got when we look at our relationship here. Weight is equal to mass times gravity. So this relationship here comes from the gradient of this graph. Now, if you're getting stuck with all this, don't worry about it, because we'll be going over this idea of gradients time and time again in year 9 and year 10, and we'll get there because it's work in progress. You are only year 8. So what you should be able to do is complete these questions now. Now, one of the questions here asks you about what kind of relationship is it. Now, it's a straight line that passes through 0, 0. So therefore, we say it's what we call directly proportional. So when this increases, this increases. So when the mass goes up, the weight goes up in proportion. But it's directly proportional because if we double the mass, we double the weight. So we double the mass, we double the weight. And that's what we mean by directly proportional. So miss out floating and sinking, and then we'll come to these questions here. You should not have a problem with these. You may have a problem with some of these calculations. So I'm just going to have a look at 33, and then we'll have our look at 37. Okay. Oh, not calc 37, sorry, 38. Okay, so 33, calculate the weight. So what we're going to do is we're going to calculate the weight of a 3 kilogram. So weight is equal to, we don't know. And it's a 3 kilogram object, so we know that mass is equal to 3 kilograms. And we have a gravitational field strength of 10 newtons per kilogram. So what that says is for every kilogram, the planet is pulling it down with a force of 10 newtons. So now, while I've been reading that, I've been writing that down here. Okay. Now, what we can now do is we can write down our formula, which is weight is equal to mass times gravity. We can now insert our numbers. So that's 3 times 10, and that will give me 30. Now, weight is a force, so that's newtons. So that is number 33, I believe. I said we were going to do 38. So if we look back at 38, we can see we're going to calculate the mass of an object. So mass is equal to question mark, I don't know. It's got of an object, it's got 600 newtons. An object with 600 newtons of force acting on it. So it's got a weight of 600 newtons, and it has a gravitational field strength of 9.8 acting on it newtons per kilogram. So I've just been writing down what I need to find out there, which is mass. I've been writing down my data, which is weight, 600 newtons, and gravity, 9.8. So now what I need to do is write down my formula. Weight is equal to mass times gravity. I now need to insert my numbers. 600 is equal to mass m times gravity, 9.8. Now, I want to make mass the subject. If I divide both sides by 9.8, what will happen is 9.8 will cancel on that side, and I will be left with 600 divided by 9.8 is equal to mass. I'll just quickly do that with my calculator. 600 divided by 9.8 is equal to 61.22. 0.224, so we'll just go 0.2. Now it's mass, so that's kilograms. Now, good luck with all these other questions that you're going to have to do. It's practice, 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 practice. Don't worry if you make any mistakes, just keep going at it. I'll post up the answers next lesson. Good luck.